Hey class, welcome back. If you check out the notes behind me on the board, here to give you a quick overview of where we've been and where we're going in the science. It's not just a rehash of what's on the notes on the blog or on Google Classroom. It's really meant to give us kind of a big view where we've been and where we're going. I'm in the quiet classroom again today. I came on in, I was writing the notes on the board, and I lost about 15 or so minutes. You'd have liked this if you were here. Would have added some humor to the class. A bird came in, and the bird immediately went up to the windows way up above. And so I spent about 15, 20 minutes trying to catch a bird in a box and get him outside. I did. It was a little house finch. But that was one of those things with me climbing around an empty classroom, standing on some tables. You probably would have at least gotten a laugh out of. If you check out the notes on the board, it's the same heading as last time. Viruses, Mutations, Jurassic Park. I don't know if we'll get to the Jurassic Park part or not today, but we'll give it a shot. And little asides over here that remind me of what I wanted to talk about. If you check out this first part right here, Christy Eifert, not a scientist name that you got to know, she's just a friend, she's a teacher, and I put her up there to remind myself. She had posted something just today on social media, Facebook, about basically the different levels of teaching. And if you check out the lowest level, it's something that she didn't use it on the thing that she posted, but Bloom's taxonomy. You don't have to look that up. But basically, it's kind of like math class. At the beginning of math class, you're learning things like your multiplication tables, adding, basic adding and subtracting. But then as you work your way up, you get more and more, hey, what can I do with this? How can I apply it? That's a little bit about what we're after here. We're learning about the basics. Okay, how does DNA work? What are the 4 bases to DNA? We're going to learn what are the 3 basic types of bacteria. But then we want to take it a little bit further. What do you do with it? I mean, how do you use this in your everyday life? With a lot of subjects, sometimes you have to kind of think about how does this really apply to what we're doing. So let's jump on in. If you look at pathogens, basically, they cause disease. If you look at the 6 basic types, some books will have 5, other books will have 7. The one that we're going to be using next trimester has 6, so that's what I'm using here. If you check out 6, the 3 that upon which we're going to focus are viruses, bacteria, and protozoa. And we certainly already talked about viruses quite a bit. A little bit about how their genetic code wrapped in a protein coat. They take over the workings of a cell, and once they take over the workings of a cell, they usually force the cell to make more copies of itself. On a personal note, I woke up yesterday, for whatever reason, not feeling great. Felt pretty bad. Matter of fact, if it was one of those days where we had students coming into school, I very likely would have tried to call in and find a substitute because I was feeling awful, which was kind of surprising. We've been doing the social distancing. I'm like, well, I haven't really been exposed to anybody. I couldn't figure out exactly what it was. I suspect it was probably something that I ate or something. Not sure what it was. I mentioned that because you start kind of going through this in your head. Okay, of the things that can infect you, of the things that can make you sick, what could it have been? Could it have been some type of virus? Is it a bacteria? Is it a protozoa? Worms, fungi, and prions are here just to make it complete. We're really going to focus on these 3 right here. I wanted to mention these 3 again, partly to make it complete. We'll talk a little bit more about fungus, of course. Prions are more recently discovered, if you will. They're kind of a very strange mechanism for getting people sick. They're a type of protein. But again, that's just very cutting edge stuff. We're going to stick with these 3 mainly in this class over the last couple of weeks that we have together. And let's talk about bacteria today. Viruses, we certainly have talked about quite a bit already. Bacteria is a good one to start with right here. And we're going to talk about strep throat. If you've ever had a really, really bad sore throat, sometimes people might say, oh, I think I have strep. I've only had strep throat that I know of one time. And I've had sore throats before, like all of us have had it one time or another. But then when I got strep throat, I was like, oh, this is what people are talking about. This is why it's so bad. It's caused by a bacteria. It's a very hardy bacteria that if somebody coughs or sneezes, you can catch it pretty easily. And the thing about bacteria is they're very tough to fight because they multiply so quickly. If you get some strep throat, streptococcus bacteria in your throat, it causes this disease. Often you need penicillin to fight it. Talk about penicillin in just a second, and a little bit about the scientific method. But the point is, when you're talking about bacteria do the same thing that viruses do in terms of they can mutate, they can change. Bacteria can reproduce under ideal conditions very quickly, sometimes as quickly as, say, 20 minutes. And they reproduce basically by just popping apart. They can make copies of themselves. However, sometimes when they make copies, they can get what's called a mutation. Getting back to our book analogy, we talked a little bit about how DNA is like the words in a book. The A, T, C's, and G's are like the letters that the DNA uses to explain to the cell how to make the protein. If you open this book, of course, there's words and paragraphs. If you look at the words and paragraphs, if I were to randomly, if I could, if this book was written, say, in pencil, and I could erase some of the words and randomly put in some letters, almost always, it wouldn't make any sense. I'd be changing some random words, and it would probably come out as gibberish. But occasionally, just by chance, every once in a while, the words that get put in randomly, if you were to change something, make better sense. They make the story better than it was before. Now, you have to wait a long time to find the change that will actually be helpful, but eventually it would happen if you're just to do it randomly all the time. This is what happens in nature with viruses and bacteria. They can change or mutate. They can mutate, and that's a random change somewhere in the genetic code. So it's making some protein a little bit differently. It's doing something differently than the previous generation did. If you look in the case of bacteria, that's really difficult to fight because they can reproduce so quickly. Quick little side trip on bacteria right here. There's a gentleman by the name of Alexander Fleming, Sir Alexander Fleming. He was knighted for his work, and he discovered penicillin. Penicillin wasn't invented, it was a discovery, and Fleming, by a lot of accounts, was somewhat careless scientist sometimes about some things, but he had great observation skills. We've talked a lot about observation skills in here as being one of the most important characteristics that a scientist can have. My personal favorite, of course, was all the things that we did on Yosemite and John Muir. Wonderful observation skills. He nailed how Yosemite was formed, where people like Josiah Whitney thought it was formed by faults. John Muir was able to use his observation skills to say, no, it looks to me very much like a glacier did this. Back to Alexander Fleming, after a 2-week vacation, he came back to his lab, and he had been working in London, ironically fighting the flu, which we're talking a lot about in here, but he was working on trying to culture those little dishes. He was trying to culture, he was trying to grow bacteria. And what had happened was some mold had gotten into one of his petri dishes. And wherever the mold had touched the bacteria had died. A lot of people, when they saw the mold, might have said, oh, my experiment's ruined, I'll clean everything, start from scratch, and start again. Sir Alexander Fleming had the presence of mind to use his observation skills and say, wait a second, I think, this is important. We found something that can kill bacteria. And you have to realize, this was just about a century ago, bacteria was taking the lives of roughly 4 out of 10 children would die of bacteria or other infections before their 5th birthday. Now, think about a world like that. When penicillin comes along, suddenly some, what we call simple, if you will, infections that can be taken care of now with antibiotics, those infections could be stopped when a person took penicillin, or at least give the body a chance to catch up. So penicillin, still the most widely used antibiotic. It's really about observation skills. Sir Alexander Fleming noticed, hey, wait a second. This is why we have to, this is what will kill the bacteria. This is what saved millions of lives since 1928. Okay, if you check out bacteria, I've drawn the bacteria here, right here, that cause strep throat, the little circles on the board with the frowny faces, of course, because they're called strep throat. And if you look at a mutation, if you look at a change in DNA, one of the things that can happen is if you take, say, penicillin for a strep throat, first day or two, you start to feel a little bit better. You start to feel a lot better. You probably, if you've ever taken penicillin before or any type of antibiotic, heard a doctor say you've got to make sure you finish the entire bottle. You've got to make sure you finish the entire dose. Sometimes when people don't, what can happen is something like this. If you're looking at the bacteria that are getting killed, that are getting wiped out by the penicillin or by the antibiotic, if by chance one or two or some happen to survive because they've got a beneficial mutation, they've got some type of change in their DNA, that is helping them survive. What can happen is when those bacteria, remember they can reproduce really quickly, when those bacteria go back to reproducing, now all their progeny, all the bacteria that came from the ones that survived will pass on that beneficial mutation. Hey, you didn't finish your penicillin, it didn't take care of all the bacteria, you feel sick again, you go back and take the penicillin again, it might not work as well the next time. That's why doctors are very, very cautious about overprescribing penicillin or any antibiotic, because if you prescribe penicillin for everything, eventually you get bacteria that can resist the penicillin, that can resist the antibiotics. We've seen this on CNN Student News, the one that we use for current events. They talk about the overprescription of antibiotics as being a very, very serious problem in biology. So if you're checking mutations, quick circle back to where we've been and where we're going. Mutations are when the DNA, the code that tells the cell what to do, what protein to make, that code gets changed usually by chemicals, by radiation, or sometimes just by natural processes. There's a genetic drift that happens naturally. But whatever the cause, when the DNA changes, the cell changes. It's not making the same exact protein perhaps anymore. It's not doing the exact same thing. In the case of viruses like COVID-19, it might change the protein code on the outside. It might make it so that the protein code on the outside makes the virus more hardy, can last longer on the surface, can attach better to a lung cell. There's a lot of changes out there that can make a virus more viable, make it survive longer in nature. The point is mutations happen all the time, and before you think, well, mutations are a bad thing, mutations really are the driving force in biology. One of the most important books, the big three that we talk about in class sometimes, is the book by Charles Darwin on the origin of species by natural selection, and natural selection, evolution if you will. But that natural selection is driven by mutations, by changes in DNA. If DNA never changes, if you've got a genetic code that stays static, that is exactly the same all the time, life can't adapt. And what we're talking about when we talk about mutations, certainly mutations are very tricky when you're dealing with things that are pathogenic, things that cause disease, viruses, bacteria. We'll talk about protozoa tomorrow. But when you're talking about biology at the high level, mutations really drive all the incredible diversity that you see in life. From the bird that flew into our classroom today that was stuck up above, up on the windows that I had to catch in a box and send outside, to the COVID-19 virus, it's all going around the world right now, to everything that you see that's living and breathing outside, it's all driven by changes in DNA over a very, very long time. We'll talk about this more next time, but that's where we're going, that's where we've been in science. Take care, miss you guys, hope to see you in class pretty soon. Bye-bye.